Right now, without any effort at all, something is holding you against your bed. You feel it as your own weight, the soft press of your body into the mattress, a pull you have lived inside every second of your life and long ago stopped noticing. We call it gravity, and we tell ourselves we understand it, the force that holds the planets, bends light, and pins the seas to the earth. But here is what almost no one is ever told. The equations Einstein wrote for that pull behave as though they secretly know about heat, about entropy, about the very same law that lets a cup of tea go cold and never warm again. At the edge of a black hole, gravity keeps the books of thermodynamics balanced to the last decimal, as if it had been rehearsing all along for a science it should know nothing about. And in 1995, one physicist showed that this is no lucky accident at the edge of a black hole, but a clue about everything that the weight holding you down may be no fundamental force at all, but something closer to warmth or pressure, a rumor of thermodynamics wearing the shape of space. There is an equivalence hiding inside your own weight tonight, and if you do not understand it, you do not understand what reality is made of. By the end of tonight, you will know exactly what it is. Before we begin, if these slow walks toward the strange edges of reality are how you like to fall asleep, a quiet like or subscribe genuinely helps the channel grow. It is a small thing for you, but it means more to me than I can easily say. Now, let's begin. There is a weight holding you against your bed right now. You can feel it if you pay attention, the soft, even pressure of your body sinking into the mattress, the pull that keeps the blanket draped over you instead of drifting off into the room. It is the most ordinary sensation in the world. It has been with you every second of your life, so constant that you almost never notice it, the way you never notice the air until the wind moves. We call this pull gravity, and we think we understand it. It holds the planets in their long, slow circles. It bends the path of light. It gathers gas into stars and pins the oceans to the earth. It is, in every physics class, the simplest of the forces to name, even if the mathematics runs deep. But tonight I want to tell you something about that weight that almost nobody is ever told, and it begins with a strange discovery. The equations that describe gravity, the ones Albert Einstein wrote down more than 100 years ago, the ones that treat gravity as the bending of space and time, turn out to behave as though they already knew about heat. Not heat in some poetic sense. Heat in the literal 19th century sense. Temperature, entropy, the slow spreading out that turns a hot cup of tea lukewarm and never turns it hot again. Somewhere in the machinery of gravity, quietly, there is thermodynamics, and no one put it there on purpose. That should stop you for a moment, because on the surface, these two things have nothing to do with each other. Gravity is geometry smooth, exact, the curve of a valley in the shape of space. Thermodynamics is the physics of crowds of trillions of jostling molecules, of randomness, of averages, of information you have given up tracking. One is the physics of the perfectly known. The other is the physics of the deliberately forgotten. And yet, when physicists looked closely at the places where gravity is at its most extreme, they kept finding the fingerprints of heat. Temperature where there should only be curvature. Entropy where there should only be shape. To feel how odd that is, think about what each kind of physics is really for. When you use gravity, when you use Einstein's equations to send a probe to another planet, or predict an eclipse 1,000 years from now, you are working in the world of the exact. Every quantity is definite. Nothing is averaged. You could, in principle, know it all. But when you use thermodynamics, you are doing the opposite. You have deliberately thrown away the details. You do not track each molecule in a cylinder of steam. You could not if you tried. Instead, you keep only a few core summaries: temperature, pressure, entropy, precisely because the underlying details are too many to hold. Thermodynamics is what physics looks like when you have surrendered to ignorance and made a science out of it. So to find thermodynamics hiding inside gravity is to find the physics of surrender hiding inside the physics of perfect knowledge. It is like discovering that the blueprint of a cathedral, drawn with a ruler to the millimeter, secretly contains a weather report. The two do not belong in the same document, and yet there they were, folded together. For a long time, the standard response to this was to file it under coincidence, or under curious but surely superficial. Gravity and heat brush against each other at the horizon of a black hole. Physicists said, but that is just a strange property of black holes, an oddity of those extreme objects, nothing that touches the rest of physics. That comfortable dismissal held up until someone refused to accept it, until someone asked whether the resemblance might be not a coincidence at the edge of a black hole, but a clue about the nature of everything. That someone is at the center of tonight's story, and the clue he followed leads directly to the weight on your own body. So here is the question that will keep us company tonight, the thread we will follow all the way down. What if gravity behaves as though it knows about thermodynamics, because gravity is thermodynamics? What if the pull holding you in your bed is not a fundamental force at all, but something more like pressure or temperature, a large-scale, statistical effect that emerges from the behavior of countless smaller things you cannot see? There is an equivalence hiding here, a place where two ideas that seemed unrelated turn out to be the same idea wearing two costumes. And I want to be honest with you about the stakes of it, because the title I gave this is not an exaggeration. If you do not understand this equivalence, you do not understand what reality is made of. By the end of tonight, you will. I am not going to hand you the answer yet. That would spoil the slow pleasure of arriving at it, and half the wonder of this story is in the arriving. What I will promise is that we will get there together, one careful step at a time, and that every step will be built from real physics, real experiments, real equations, real people who sat with these ideas until the ideas cracked open. We will start with black holes, because that is where the strangeness first showed itself. We will watch a young physicist, in the middle of the 1990s, notice something so odd that it changed how a generation thinks about space itself. And we will end back here, in this room, with the weight against your body, seeing it in a way you have never seen it before. For now, just hold on to the strangeness. Gravity, the smooth and geometric and perfectly known force, keeps acting as if it has a secret, as if, underneath the curve of space, it is quietly doing accounting, balancing books, keeping track of heat, and the first place anyone caught it in the act was at the edge of the darkest objects in the universe. To see why gravity looks like it knows about heat, we have to go to a black hole, and we have to go back about 50 years, to the early 1970s. At that time, a black hole was understood as almost aggressively simple. You take enough matter, pack it tightly enough, and gravity wins so completely that nothing, not even light, can escape from a certain boundary around it. That boundary is called the event horizon. It is not a solid surface. It is a line in space, a point of no return, and once you cross it, every path you could possibly take leads inward. The remarkable thing physicists believed back then was that a black hole, no matter how it formed, could be described by just a few numbers: its mass, its spin, and its electric charge. Everything else, the star that collapsed, the light that fell in, the encyclopedias and pianos and planets that crossed the horizon, all of it seemed to vanish into those few numbers. The physicist John Wheeler summarized this with a phrase that stuck: a black hole has no hair. It is bald, featureless, almost insultingly plain. But a young graduate student named Jacob Bekenstein noticed a problem with that plainness, and the problem was about entropy. Entropy is one of those words that sounds more intimidating than it is. At its heart, entropy is a measure of how many different ways the hidden details of a thing could be arranged without changing how it looks from the outside. A shuffled deck of cards has high entropy because there are astronomically many orders the cards could be in. A sorted deck has low entropy because there is essentially only one way to be perfectly sorted. And the second law of thermodynamics, one of the most reliable statements in all of science, says that the total entropy of the universe never decreases. Left to itself, the world always moves from order toward disorder, from the sorted deck toward the shuffled one, from the hot coffee toward the cold. Never the other way. Bekenstein asked a dangerous question. What happens to the entropy when you throw something into a black hole? Suppose you take a cup of hot tea, a nice bundle of entropy, all that molecular jostling, and you drop it past the event horizon. From the outside, the black hole just gets very slightly more massive and stays bald. The tea's entropy is gone from the universe. But the second law says entropy cannot simply disappear. So either the law is broken at the edge of a black hole, or the black hole itself must carry entropy, must absorb the entropy of everything it swallows, and keep it on the books somehow. Bekenstein made the bold claim that a black hole does exactly that, and that its entropy is proportional not to its volume, the way you might expect, but to the area of its event horizon. The bigger the surface of the hole, the more entropy it hides. This was a strange enough idea, but it had a consequence that at first seemed to sink it. If a black hole has entropy, then by the underlying logic of thermodynamics, it must also have a temperature. And if it has a temperature, then it must radiate everything with a temperature glows, gives off energy, the way a hot iron glows red. But a black hole was supposed to be the one thing in the universe that could not give off anything at all. That was the whole point of it. So most physicists assumed Bekenstein had made a clever mistake. Then Stephen Hawking, in 1974 and 1975, did the calculation that made it real. Working through the behavior of quantum fields right at the edge of the horizon, Hawking found that a black hole does radiate, faintly, with a very precise temperature, and that the temperature depends on the mass in a way that feels almost backwards. The bigger the black hole, the colder it is. A black hole with the mass of our Sun would be far colder than the empty space around it, radiating so faintly it would take a length of time beyond all imagining to fade. But radiate it does. The radiation now carries Hawking's name. And it confirmed Bekenstein. The entropy of a black hole really is 1/4 of the area of its horizon, measured in the tiniest natural units physics has, the Planck units. That simple little fraction, the area, divided by 4, became one of the most quietly important formulas in modern physics. It is worth pausing to feel how much entropy that fraction represents, because the numbers break the imagination in a way that matters for the rest of the night. Entropy, remember, is a count of hidden arrangements of how much information is locked away out of sight, and a black hole turns out to hide far more information than the ordinary matter that made it. If you took the Sun and let it collapse into a black hole, the entropy of the resulting hole would be some 20 times greater than the entropy of all the hot gas of the Sun that went into it, and the Sun's entropy was already an almost unspeakably large number. A black hole is, by an enormous margin, the most information-dense object the universe permits. Whatever falls in is not simply crushed, its hidden information is stored, in quantities that dwarf anything we know how to build, written somehow onto that dividing surface. Bekenstein's insight was not just that black holes have entropy, it was that they have more of it than anything else, that they are the universe's great reservoirs of hidden information, and that the reservoir is measured by area. And notice the quiet oddity in that last word, because it will grow into one of the central mysteries later tonight. The entropy of ordinary things scales with volume. A room holds twice the air and hides roughly twice the information. A bigger box of gas has proportionally more hidden arrangements inside it. That is how information normally works. It fills a space. But a black hole's entropy scales with the area of its surface, not the volume it encloses. Double the surface, double the hidden information, but the inside, the sheer interior volume, does not enter the count at all. It is as though everything a black hole hides is written on its skin rather than stored in its belly. Hold onto that strangeness. It is the first whisper of an idea that the information content of any region of space might be set by its boundary rather than its bulk, and that whisper will return much later as one of the loudest clues we have about what space really is. Now watch what happens, because this is the moment the books start to look suspicious. A black hole that radiates is a black hole that is slowly losing mass. And a black hole that loses mass has a shrinking horizon. And a shrinking horizon means shrinking area, which, by Bekenstein's rule, means shrinking entropy. The black hole's own entropy is going down. But the second law says the total entropy of the universe can never go down. So the only way the books can balance is if the Hawking radiation flooding outward carries away at least as much entropy as the black hole loses. And here is the delicate part, the part that should not work as neatly as it does. For that outgoing radiation to carry the right amount of entropy, there has to be a matching flow of negative energy crossing inward through the horizon, feeding the shrinkage. And the exact relationship between that energy flow across the horizon and the change in the horizon's area is governed by, of all things, Einstein's equation for gravity. Sit with that. The second law of thermodynamics stays intact during black hole evaporation only because Einstein's purely geometric equation for gravity delivers precisely the right bookkeeping to make it work. A law about heat is kept safe by a law about the shape of space, and the two mesh together so perfectly that you would swear they had been designed as a matched set. As the physicist Ted Jacobson would later put it, it is as if classical gravity already knew it had to be prepared for Hawking radiation. As if geometry had been quietly rehearsing for thermodynamics all along, long before anyone knew the two had anything to say to each other. That phrase is worth holding on to, because it is the crack through which everything else will come, as if gravity already knew. When two parts of physics fit together that snugly, a scientist starts to suspect they are not really two things at all. Maybe the reason gravity knows about thermodynamics is not some cosmic coincidence, not some lucky matching of separate laws. Maybe gravity knows about thermodynamics because, underneath, it simply is thermodynamics. But black holes are exotic and rare. To turn this suspicion into something real, someone would have to show that the same secret hides not just at the edge of a black hole, but everywhere in the empty space of this very room. And that is exactly the leap we are about to take. The trouble with black holes is that they are special. There is a black hole at the center of our galaxy, and there are others scattered through the universe, forming and merging and slowly evaporating. But they are particular places, dramatic and distant. If the marriage of gravity and thermodynamics only showed up at the edge of a black hole, you could shrug it off as a quirk of those strange objects, a rule that applies to the deep end of the pool and nowhere else. For the equivalence we are chasing to mean anything about reality, about your reality, it would have to be true everywhere. It would have to be as true here, in the ordinary air above your bed, as it is at the rim of a collapsed star. So the question becomes, is there a way to see an ordinary point in empty space as if it was sitting on the edge of a black hole? And the surprising answer is yes, you only have to move the right way. This is where we meet an idea called the horizon of an accelerating observer. And to feel it, we have to slow down and build the picture carefully, because it is one of the loveliest and strangest ideas in physics. Imagine you are floating in perfectly empty space. Nothing is nearby, no stars, no walls, just you and the smooth, flat emptiness that physicists call Minkowski space, the space of ordinary relativity with no gravity in it at all. Now imagine you start to accelerate. You fire a little engine and speed up, faster and faster, in one direction, and you keep it up forever. Something remarkable happens behind you. Because nothing can travel faster than light, and because you are forever gaining speed, there comes to be a region behind you from which light can never catch up to you. A signal sent from far enough back, even a beam of light racing at full speed, will always be chasing a target that keeps pulling away. That region, you can never receive anything from that boundary, beyond which the universe is causally sealed off from you, is a horizon. It is called a Rindler horizon, after the physicist Wolfgang Rindler, and it behaves in a startling number of ways, exactly like the event horizon of a black hole. But this horizon is not made of collapsed matter. It is made of nothing but your own acceleration. If that sounds too convenient, like a trick of definitions, there is a profound principle underneath it that Einstein himself considered the happiest thought of his life. It is the equivalence principle, and it says that acceleration and gravity are, locally, the very same thing. Stand in a sealed room on the Earth's surface, and you feel your weight. Ride in a sealed rocket, accelerating through empty space, and you feel an identical pull, indistinguishable in every measurement you could make inside the room. There is no experiment that can tell steady acceleration apart from standing still in gravity. So if a real gravitational horizon, the edge of a black hole, has a temperature and an entropy, then it should not be surprising. It should be almost required that an accelerating observer's horizon carries the same properties. The equivalence principle practically insists on it. Acceleration is gravity in disguise, and so the horizon it conjures inherits gravity's strange thermodynamic wardrobe. This is why the local horizon is such a powerful idea. It lets you carry the exotic physics of a black hole into the most ordinary corner of empty space, simply by imagining an observer who accelerates through it. You do not need a collapsed star. You need only motion, and the equivalence principle does the rest, guaranteeing that the same rules of temperature and entropy that rule the black hole must also, quietly, rule the empty air. Now let me place you at a single point in that flat, empty space, and let me show you the geometry the way a physicist sees it, because it will matter later. Through your point, draw the paths that light would take. In the simplest picture, with one direction of space and one direction of time, the light rays form a great X1 ray, going up and to the right, one going up and to the left, and their mirror images below. That X is the light cone, the map of what can affect what. And that X carves the space around your point into 4 wedges, like the 4 triangular slices you would get by cutting an hourglass through the middle. Take just one of those wedges, say, the one opening to the right. It has a beautiful hidden symmetry. You can slide the whole wedge along itself, a kind of stretching rotation that mathematicians call a boost, and it maps the wedge perfectly onto itself. Every accelerating observer we just imagined is really just riding along one of the curved tracks of this single flowing symmetry. Closer to the center point, the tracks curve harder, meaning higher acceleration. Farther out, they curve gently, meaning gentler acceleration. But all of them together form one smooth flow through the wedge, and the edges of that wedge, the arms of the light cone X, are the horizon. Here is the immersive thing I want you to try, lying there in the dark. Picture the point at the center of your own chest as that special point. Through it run the light rays, the great, slow X of causality, dividing the space around you into those 4 wedges. Feel how the ordinary, unremarkable spot where you are resting, the spot that seems like nothing, like empty air and a mattress, has exactly the same causal structure as the edge of a black hole. There is a wedge of the universe you could seal yourself off from simply by accelerating away from it. There is a horizon latent in every point, waiting for the right motion to reveal it. You do not have to travel to a black hole to stand at a horizon. You are already, in a sense, that will become more literal as the night goes on, sitting on the edge of one. Every point in space is. This was Ted Jacobson's crucial move, and it is worth admiring how simple it is once someone has thought of it. Instead of studying the one grand horizon of a black hole, he decided to treat every point in spacetime as though it sat on the horizon of a little black hole, a local horizon, seen by an observer accelerating through that point. If the relationship between entropy and energy that Bekenstein and Hawking found for a real black hole horizon also held for these tiny local horizons, at every point, in every direction, then gravity's secret would not be a quirk of black holes. It would be woven into the fabric of space everywhere. The plan was audacious in its plainness. Take the thermodynamics of horizons, demand that it hold at every point of the universe, and see what the demand forces to be true. But to actually run that argument, Jacobson needed one more ingredient, and it is the strangest ingredient of all. He needed the empty vacuum of space itself to have a temperature. He needed to show that nothing genuine, star-free, particle-free nothing is quietly, secretly warm, and that is where the story leaves geometry behind for a while and steps into the quantum world, where the emptiness turns out to be nothing like empty. We have a habit of thinking of empty space as the absence of things. You take a box, you remove all the air, all the light, all the particles, and what remains is the vacuum nothing, the blank stage on which the drama of physics plays out. It is one of the most natural pictures in the world, and it is wrong in a way that took physicists most of the 20th century to fully appreciate. The vacuum of quantum physics is not an absence. It is a presence. It is the lowest energy state of the quantum fields that fill all of space. And being the lowest energy state does not mean being empty. It means being as quiet as the fields are allowed to be, and the rules of quantum mechanics do not allow them to be perfectly still. There is always a faint restlessness, a trembling that can never be removed, because removing it entirely would violate the uncertainty that sits at the heart of quantum theory. Now, here is the fact that should genuinely unsettle you, and it is not speculation. It is one of the more firmly established results in all of quantum field theory. Whether the vacuum looks empty or looks warm depends on how you move through it. To an observer floating freely, drifting without acceleration, the vacuum is the vacuum, cold, quiet, the lowest state there is. But to an observer who is accelerating riding one of those curved tracks through the wedge we drew a moment ago, that very same vacuum glows. It fills with a faint thermal radiation, a genuine warmth with a genuine temperature, and the temperature is proportional to how hard the observer accelerates. This is called the Unruh effect, named for the physicist William Unruh, who worked it out in the 1970s. Accelerate gently, and the vacuum is barely warm. Accelerate ferociously, and it heats up. The nothing has a temperature, and the temperature is written in your motion. There is a companion result, with a heavier name, the Bisognano-Wichmann theorem, that says the same thing in a cleaner and even more startling way, and I want to give it to you slowly, because it is the hinge of the whole night. Take the quantum vacuum, the true lowest energy state, filling all of space. Now, purely in your imagination, draw a flat plane straight through space and decide to pay attention only to one side of it. Do not build anything. Do not place a wall. Just mentally divide space into two halves, a left and a right, and agree to consider only what happens on the right, ignoring everything on the left. The theorem says that the vacuum, restricted to that one half, is no longer the quiet, lowest energy state. It is a thermal state, a warm, restless state of the kind you would find in an oven at some temperature, where different energy levels are occupied with different probabilities, the higher energies rarer, falling off in the smooth, exponential curve that describes heat everywhere in physics. By the simple act of not looking at half of space, you have turned the vacuum into a furnace. Let me make this something you can feel, because this is one of the seen moments of the night, the kind of thing best experienced lying still with your eyes closed. Picture the room you are in. Picture a single flat plane, like an enormous invisible sheet of glass, sliding down through the middle of it, through the walls, through the air, through the space just above your body, dividing the room into a near half and a far half. Nothing physical has changed. No membrane has appeared. The air is still just air. But according to the physics, if you consider only the vacuum on your side of that plane, taken entirely on its own, it is now a warm bath. It has a temperature. It faintly seethes with thermal energy that was in no way there a moment ago. Energy you conjured not by adding anything, but purely by drawing a line and choosing a side. The warmth was hiding in the act of separation. The imaginary wall, remember that phrase, the imaginary wall, because we will return to it when it matters most. The imaginary wall is where the heat comes from, and it is made of nothing but a decision about what to ignore. What kind of heat is this, exactly? What is the energy that this warmth is measured against? This is a subtle point, but a beautiful one. The ordinary energy we know, the energy that is conserved, because the laws of physics do not change from moment to moment, the energy that runs your body and lights the stars, that is energy tied to marching straight forward through time. But the warmth of the restricted vacuum is measured against a different kind of energy, one tied not to marching forward through time, but to that stretching rotation, that boost flow we drew through the wedge. Physicists call it the boost energy. It is a perfectly real conserved quantity, just tied to a different symmetry, the hyperbolic turn of the wedge, rather than the straight arrow of ordinary time. And the vacuum, restricted to one side of the imaginary wall, is precisely a warm, thermal state with respect to that boost energy. The heat is real. It is simply keyed to a stranger clock than the one on your wall. I want to guard against a misunderstanding here, because it is easy to hear all this and think it is some illusion or trick of perspective, a mere accounting fiction. It is not. The Unruh warmth is, in principle, a real temperature that a real accelerating detector would register a genuine bath of particles, where a non-accelerating detector would find only silence. Two observers, one drifting and one accelerating, through the very same patch of vacuum, would honestly disagree about whether there is warmth there at all, and both would be right. This already tells you something profound and slightly vertiginous about reality. Even the question of how many particles are present, whether a region is empty or full, does not have a single absolute answer. It depends on how you move. The vacuum is not a fixed thing that everyone agrees on. It is relative to the observer, in the deepest sense, and the disagreement is not about opinions, but about physical facts that both parties can measure. Let that sink in for a moment, resting there in the dark, because it overturns something you have carried your whole life without questioning. You have always assumed that emptiness is emptiness, that if a region has nothing in it, then it simply has nothing in it, full stop, for everyone. But the physics says the fullness of space is in the eye of the mover. Accelerate, and the nothing fills with warmth. Coast, and it empties again. The same space, the same instant, holds both truths at once. And it is precisely this slippery, observer-dependent warmth that will serve as the temperature in the great derivation to come. Notice what has quietly happened here, because it is the reason this long detour matters. We now have, sitting in the empty vacuum of any region of space, all three of the ingredients that made black holes so suspicious. We have a horizon, the edge of the wedge, the Rindler horizon that any accelerating observer carries with them. We have a temperature, the Unruh warmth, the thermal character of the restricted vacuum, and in the next part we will find the third ingredient, the entropy, hiding in the same place. The thermodynamics that seemed to belong only to black holes is turning out to be a property of nothing at all, of plain, undramatic, everywhere emptiness, the emptiness a centimetre above your resting hand. But a temperature, on its own, is only 2/3 of the story. Heat without entropy is a fire without fuel. So we have to ask the next question, the one that takes us to the very bottom, where, in the empty vacuum, is the entropy. What exactly is doing the hiding, and what is it hiding from? The answer is a kind of connection that Einstein himself called spooky. We have found a temperature in the empty vacuum, but a temperature is a strange thing to find in nothing. Temperature is supposed to be a property of a crowd of many particles sharing energy, bumping and mixing until the energy is spread out. Where is the crowd in empty space? Where is the randomness coming from when the vacuum is, by definition, the most orderly and definite state there is? To answer that, we have to talk about entanglement, which is the deepest and most genuinely bewildering feature of quantum mechanics, and which turns out to be the hidden fuel underneath the whole story. Let me start with the simplest possible example, the one physicists reach for because it strips the mystery down to its bones. Imagine two tiny particles, each carrying a property called spin. You can picture spin, loosely, as a little arrow that can point up or down when you measure it. Now prepare these two particles in a special shared state, a state physicists call a singlet, in which their spins are perfectly opposite, but neither one has decided which way it points. This is the part that breaks intuition. It is not that one particle is secretly up and the other secretly down, and you simply do not know yet. It is that neither particle has a definite direction at all, and yet the two are bound together so that whatever one turns out to be, the other will always be the opposite. The pair has a definite relationship without either member having a definite state. That is entanglement. Now watch what happens when you can only see one of them. Suppose the two particles fly apart, and you keep just one, while the other drifts away across the room, across the country, across the galaxy. The distance does not matter. You measure your particle's spin. You find it points up, but before you measured it, it had no direction. The up appeared, genuinely random, at the moment of measuring. If you had many such pairs, and measured only your halves, you would find a perfectly random sequence up, down, up, with no pattern at all. Your particle, taken by itself, is a coin flip. All of its definiteness lives not inside it, but in its relationship with the partner you can no longer see. And there is a precise amount of hidden information in that arrangement, exactly one bit, one yes or no's worth of uncertainty, because there are two equally likely outcomes. In the language of entropy, that one bit is the logarithm of 2 the smallest non-trivial entropy there is. This is entanglement entropy, the uncertainty that appears in one piece of a system precisely because it is entangled with a piece you are not looking at. This connection between the two particles bothered Einstein so much that he gave it a famous and slightly contemptuous name, spooky action at a distance. He could not accept that two particles, separated by any distance at all, could share a bond this intimate, with neither one carrying a definite answer until the moment of measurement. He suspected there had to be hidden instructions, secret settings carried by each particle from the start, that only made the correlation look mysterious. But decades later, beginning with the work of John Bell in the 1960s, and confirmed in experiment after experiment since, physics delivered its verdict, and Einstein was wrong on this one point. There are no hidden instructions. The correlation is real, and it is deeper than any prearranged answer could produce. Entanglement is a genuine feature of the world, not a gap in our knowledge. Two entangled things share a single, indivisible state, and the definiteness of the whole simply does not live in the separate parts. I want to be precise about one thing, because it is a common and understandable confusion. This connection cannot be used to send a message faster than light. If you hold one particle, and I hold its partner across the galaxy, I cannot wiggle mine to signal you, because all you ever see on your end is randomness. The pattern only reveals itself later, when we bring our two lists of results together and compare. So entanglement does not break the cosmic speed limit. It carries no signal. What it carries is something subtler and, For our purposes tonight, far more important. Correlation without communication, a shared definiteness spread across a divide, hidden from anyone who can only see one side. And the quantum vacuum, it turns out, is drenched in exactly this kind of hidden correlation at every point across every surface you could imagine drawing. Now carry that idea back to the imaginary wall, the plane we drew through the room. The quantum vacuum is not made of two spins. It is made of fields, the electron field, the electromagnetic field, and the rest spread continuously through all of space. But a continuous field can be broken up into pieces, into modes, each one like a simple vibrating system, a tiny oscillator that can hold different amounts of energy. And here is the crucial thing. For every one of those little oscillating modes on your side of the imaginary wall, there is a partner mode on the other side, and the two are entangled exactly like the two spins. But now it is the amount of energy in the mode, its occupation, that is correlated across the divide. The vacuum, taken as a whole, is a single, perfectly definite quantum state, as definite as anything in physics. But it is stitched together out of countless entangled pairs straddling every possible dividing surface you could draw. So now you can see where the warmth comes from. When you restrict your attention to one side of the imaginary wall, you are throwing away your access to all those partner modes on the other side. And the moment you lose the partners, the definiteness of your side dissolves, just as your single spin became a coin flip when its partner drifted away. The perfectly definite, orderly vacuum, cut in half and viewed one side at a time, becomes uncertain, mixed, random, and that randomness has a temperature. The heat of the restricted vacuum is not the jostling of particles. It is the blurring that comes from cutting entanglement threads and losing half of every pair. The warmth is correlation you can no longer see. The furnace on your side of the wall is lit by the connections you gave up when you chose a side. I want to let that settle, because it inverts something most of us carry without noticing. We tend to think emptiness is simple and matter is complicated. But the vacuum, it turns out, is threaded through and through with entanglement, a dense weave of correlations linking every region to every neighboring region, at every scale, down as far as you can look. Empty space is not the absence of structure. It is one of the most intricately connected things there is. And the entropy of a region, the hidden information you lose when you seal that region off behind a horizon, is a measure of how much entanglement you have cut. This is the third ingredient, the one we went looking for. Horizon, temperature, and now entropy, all of them present not just at the edge of a black hole, but in the empty air of any room, waiting in the correlations of the vacuum. Here is why this matters so much for where we are going. When Jacobson set out to demand that the thermodynamics of horizons hold at every point in space, the entropy in his equation was not going to be some vague abstraction. It was going to be this, the entanglement entropy of the vacuum across a local horizon, the count of correlations severed by the wall. And the heat was going to be the boost energy flowing across that horizon. He had, sitting in the empty vacuum, a temperature and an entropy, and a horizon, all three, all real, all deriving from the quantum connectedness of nothing. The only thing left to do was to write down the same simple thermodynamic relation that has governed heat since the 1800s, demand that it hold at every point, and see what fell out. What fell out was gravity. That is the moment we turn to next, and it is the beating heart of the whole night. The year is 1995. To understand the size of what is about to happen, you have to hold in your mind how separate the two halves of this story still seemed. On one side, there was gravity, Einstein's masterpiece, general relativity, the theory that describes gravity as the curvature of spacetime. Its central statement is the Einstein field equation, And though the mathematics is intricate, its meaning is almost sculptural. Matter and energy tell spacetime how to curve, and the curve of spacetime tells matter how to move. It is geometry, pure and exact and deterministic. On the other side, there was thermodynamics, the physics of heat and entropy, and the second law, the physics of steam engines and shuffled cards and forgetting. For 100 years, these had lived in different chapters of the textbook, different buildings on the campus, different corners of the mind. One was the physics of the perfectly known, the other was the physics of the deliberately averaged. Ted Jacobson took the three ingredients we have, assembled the local horizon at every point, the Unruh temperature of the accelerating vacuum, and the entanglement entropy proportional to horizon area, and he did something with them that had the audacity of a magic trick performed in broad daylight. With the audience invited to inspect every step, he reached for the oldest and humblest relation in all of thermodynamics, the one that says heat added equals temperature times change in entropy. Physicists write it as delta Q equals TdS. It is called the Clausius relation, after Rudolf Clausius, who wrote it down in the middle of the 1800s, long before anyone knew what atoms were, long before quantum mechanics, long before black holes. It is the relation that defines what entropy even means in terms of heat. It is about as fundamental and about as old-fashioned as thermodynamics gets, and Jacobson simply demanded that this relation hold. Not for a steam engine, not for a black hole. For every one of those tiny local horizons, at every single point in spacetime, in every direction you could orient the horizon, take a point. Take an accelerating observer passing through it, carrying their little Rindler horizon. There is heat flowing across that horizon energy, boost energy, the flux of matter and fields streaming through it. There is a temperature, the Unruh temperature of that accelerating frame. And there is an entropy 1/4 of the horizon's area, the entanglement entropy of the vacuum being cut. Now insist that the heat, the temperature, and the entropy obey Clausius's 2-100-year-old relation, delta Q equals TdS, at that point, and at the next point, and at every point, for every possible horizon through each of them. When Jacobson worked out what that demand requires, what the geometry of spacetime has to be doing in order for this thermodynamic bookkeeping to balance everywhere, in all directions, at once the answer that came out was Einstein's field equation, not something like it, not an approximation to it. The equation itself, the exact law of gravity, emerged as the necessary condition for the Clausius relation to hold on every local horizon. Gravity was not assumed anywhere in the argument. Geometry was not put in by hand. Jacobson started with heat and entropy and temperature with thermodynamics, and gravity fell out the other end as a consequence. Let me try to give you the moment itself, the way it might have felt, because moments like this are rare in a scientific life. Picture a physicist at a desk, following the black hole bookkeeping downward, not up toward the grand and distant horizon of some collapsed star, but down into the ordinary, into every point of empty space, applying the same little relation Clausius wrote by candlelight to the trembling, entangled vacuum. Picture the algebra assembling itself, term by term, the way a pressure law assembles out of the blind collisions of gas molecules, and picture the instant of recognizing the shape of the result. That is Einstein's equation. The most celebrated equation in the physics of gravity, the one carved on memorial walls and printed on the first page of every relativity textbook, revealing itself to be, underneath, a thermodynamic identity, an equation of state. As if gravity already knew about thermodynamics because gravity, it now appeared, simply was thermodynamics, wearing the costume of geometry. I called this an equation of state, and I want to make sure that phrase lands, because it is the exact and careful way physicists describe what Jacobson had shown. You already know an equation of state, even if you have never heard the term. The ideal gas law, pressure times volume, equals a constant times temperature. The relation you may have met in a chemistry class is an equation of state. It relates the big, bulk, sloshing properties of a gas, its pressure, its volume, its temperature. And notice what an equation of state does not mention. It says nothing about any individual molecule. It does not track a single atom's path. It is a statement purely about the averaged, collective behavior of an unimaginable number of tiny things, whose details you have given up following. It is a law of the crowd, not a law of the members. When you say gravity is an equation of state, you are saying gravity is like that a law about the collective, averaged behavior of some immense number of underlying things, not a fundamental force in its own right. The curvature of spacetime would be to those hidden things what pressure is to the molecules of the air, real, lawful, measurable, and yet emergent, a large-scale summary of something smaller and more numerous underneath. It helps to see just how closely the whole argument shadows the way you would derive the ideal gas law itself, because the parallel is what convinced Jacobson he was really onto something rather than fooling himself. To get the gas law, a physicist needs 3 ingredients. First, they need to know how the entropy of the gas depends on its energy and the space it occupies. Second, they need the fact that energy is conserved. It does not vanish or appear from nowhere. And third, they need the Clausius relation, the rule connecting how much heat enters or leaves to how much the entropy changes at a given temperature. Put those 3 together, and out comes the equation of state, pressure, and volume and temperature bound in a single law. Jacobson did the very same thing, ingredient for ingredient, but for a patch of space. In place of the gas's entropy, he used the entropy of a local horizon, which is its area. In place of energy conservation, he used the precise mathematical statement that the energy and momentum of matter are locally conserved. And in place of ordinary heat, he used the boost energy flowing across the horizon, with the Unruh temperature as the temperature. Feed those in, demand the Clausius relation, and out comes not a law about gases, but Einstein's law of gravity. Same recipe, same 3 ingredients, same ancient thermodynamic logic, applied to spacetime instead of steam, and yielding the geometry of the universe. There is one subtlety worth naming, because it is quietly profound. The heat in this derivation is not ordinary heat, and the energy is not ordinary energy. It is boost energy that's stranger quantity, tied to the hyperbolic stretching flow of the wedge, rather than to marching forward in time. In a sense, Jacobson had to discover which clock the vacuum keeps its thermodynamic books against, and it was not the clock on your wall. It was the peculiar clock of an accelerating observer, the clock of the horizon. Once he tuned the thermodynamics to that clock, everything clicked into place. It is as if gravity had been keeping a ledger all along, but in a currency and a calendar we had never thought to check. This is the emotional center of the whole night, so let me say it as plainly as I can without the softening. If Jacobson is right, then gravity, the weight holding you in your bed, the force that shapes galaxies and bends light and set the planets on their courses, may not be one of the basic building blocks of nature at all. It may be a rumour of thermodynamics, the same kind of thing as the warmth of a room or the pressure of the air, not fundamental but statistical, an average that emerges when you stop tracking the details. The floor of physics, the bedrock you thought you were standing on, turns to water. The equation you were told describes the underlying structure of space and time, turns out to be an accounting identity for heat and information. The same species of law that governs a candle burning down and a cup of tea going cold. Now, I owe you some honesty here, the kind Jacobson himself insists on, because he is careful about his own result in a way that makes it more trustworthy, not less. This derivation is a remarkable and rigorous piece of reasoning, but it comes with what he calls interpretive fuzziness. To make the argument work, you have to be careful about exactly what you mean by the heat, and exactly how you define these local horizons, and there are subtleties that mathematicians and physicists still argue over. It does not, by itself, prove that spacetime is made of tiny atoms of something. What it proves is more like a powerful clue, that whatever gravity turns out to be, it wears the form of thermodynamics, so exactly that the resemblance can hardly be an accident. It is the formula that works. And in physics, as we will see near the end of the night, a formula that works even before anyone understands why has a habit of dragging the entire field toward a revolution. But before we get there, we have to face a problem that this whole picture created, an infinity so severe it threatened to sink the idea entirely. And the way that infinity gets tamed is one of the most elegant turns in the story. There is a crack in the beautiful picture we have built, and honest physics does not paper over its cracks. It walks straight into them, because that is usually where the next idea is hiding. The crack is this. We said that the entropy of a region is the entanglement entropy of the vacuum across its boundary, the count of correlations you sever when you draw the imaginary wall. That sounds fine until you try to actually count them, and then it goes catastrophically wrong. Because when you add up all the entanglement across a surface, in ordinary quantum field theory, the answer you get is not large. It is infinite. Here is why. Remember that the vacuum's entanglement lives in those little modes of the field, the tiny oscillators paired across the wall. The trouble is that there is no smallest mode. You can have modes of any wavelength, any size, right down to the infinitely small. And the entanglement piles up most densely exactly where the two sides of the wall come closest together, packed right against the dividing surface, in ever finer detail, at ever shorter distances. As you look closer and closer to the boundary, you find more and more entangled pairs, smaller and smaller, without limit. Add them all up, and the entanglement entropy of any surface, in plain quantum field theory, diverges to infinity. There is no shortest wavelength to stop the sum, because the ordinary rules of relativity and quantum mechanics allow the field to fluctuate on any scale, no matter how tiny. Now put that beside what we actually know about black holes. The Bekenstein-Hawking entropy of a black hole is not infinite. It is a specific finite number, 1/4 of the horizon's area, measured in Planck units. A black hole the size of a city has an entropy that is almost unthinkably larger in hidden information than every hard drive and every book and every computer memory humanity has ever built, all combined many times over, but it is finite, definite, countable in principle. So we have a stark contradiction. The entanglement picture says the entropy across any horizon should be infinite. The black hole says it is finite and equal to the area over 4. If entanglement entropy is really what black hole entropy is, something has to intervene to cut the infinity down to exactly the right finite size. Something has to reach in at the very smallest scales and stop the counting. What could possibly do that? The answer is the hero of our whole story, showing up again in a new role, gravity. And the argument for how gravity does it is one of those ideas that is simple enough to feel in your body once someone slows it down. Think about those troublesome modes, the ones causing the infinity, the smallest ones, packed closest to the wall. By the rules of quantum mechanics, the smaller you localize something, the more uncertain and the larger its energy becomes. Squeeze a fluctuation into a tinier and tinier space, and its energy climbs higher and higher. So, the modes responsible for the infinite entanglement are not gentle. They are the highest energy, most violently concentrated fluctuations there are, crammed into the smallest spaces right against the boundary. But energy, is not a passive bystander in this universe. Energy gravitates. Energy curves space-time. That is the whole content of everything we have been discussing. And so, if you take gravity seriously, if you remember that these ferocious little high-energy fluctuations are themselves sources of gravity, something has to give at the smallest scales. When a fluctuation and its entangled partner are squeezed close enough together, their own concentrated energy warps the space-time around them so strongly that they wrap themselves in a tiny horizon of their own, a miniature event horizon engulfing the pair. And once that happens, you can no longer even say which side of the imaginary wall each partner is on. The very notion of the dividing surface goes fuzzy, uncontrollable, meaningless, right at the shortest distances. The wall, which we treated as a perfectly sharp plane, dissolves into vagueness at the bottom. So gravity cuts off the infinity, not by adding some arbitrary rule, but as a natural consequence of taking its own effect on the tiniest fluctuations seriously. Below a certain scale, there is simply no more counting to be done, because there is no longer a well-defined wall to count across. And here is the part that gives the whole idea its quiet triumph. When you estimate where that cutoff falls, the scale at which gravity blurs the wall and stops the sum, you can argue, in a rough and hand-waving but genuinely compelling way, that it lands exactly where it needs to, reproducing the finite Bekenstein-Hawking value, the area divided by 4. The infinite entanglement of the vacuum, trimmed by gravity's action on its own smallest fluctuations, comes out to precisely the entropy of a black hole. The two pictures, which seem to contradict each other, turn out to be the same picture, reconciled by gravity policing the infinite. The scale at which gravity steps in to do this trimming has a name and a size, and the size is worth sitting with because it is where all of tonight's strangeness ultimately lives. It is called the Planck-length, and it is about 1.5 times 10 to the minus 35 meters. That string of words hides a smallness the mind cannot really hold, so let me try to stretch it out. If you took a single atom and blew it up to the size of the entire observable universe, then the Planck length, blown up by that same enormous factor, would still be smaller than an average tree. It is as far below the size of an atom as an atom is below the size of the cosmos, and then some. This is the depth at which the smooth fabric of space is thought to come apart, where the imaginary wall goes irreparably fuzzy, where the fierce little fluctuations wrap themselves in their own horizons. Everything we experience, every ruler, every wavelength of light, every particle physicists have ever detected lives enormously far above this scale, up in the smooth, well-behaved country where space looks continuous and gravity looks gentle. The Planck length is the cellar of reality, and we have never been down there. We only know, from arguments like this one, that something must change when we arrive. That is a humbling and beautiful place for the argument to have led. We started by asking where the entropy of empty space could possibly come from, and we have ended at the Planck length, at the very floor of the world, watching gravity reach down into the smallest imaginable distances to keep the books of the universe finite. The same force that holds you in your bed is, at this unthinkable depth, quietly setting the limit on how much reality a region of space can contain. Step back and feel the shape of what just happened, because it is almost circular in the most beautiful way. We used the thermodynamics of the vacuum to derive gravity, and now we are using gravity to make the thermodynamics of the vacuum finite and consistent. Gravity emerges from the entanglement entropy, and gravity is also what keeps the entanglement entropy from blowing up. The two are not layered one on top of the other, like separate floors of a building. They are wound around each other, each one holding the other in place, which is exactly what you would expect if they were, at bottom, the same thing seen from two sides. We have now assembled every piece of the core argument, and that means it is time to stop, take a breath, and lay all the pieces out on the table together in plain sight, before we ask the question that will carry us into the second half of the night, the question of what, if gravity is the equation of state, gravity is the equation of state of. Let us slow down here and gather everything, the way you might stop halfway up a long trail to look back at the country you have crossed. We have come a fair distance from the weight against your bed, and the path had some steep and strange stretches, so it is worth standing still for a moment and letting the whole shape of the argument come into view at once, calmly, with nothing new added. If you have drifted at all, and it is perfectly all right if you have, this is exactly the kind of thing meant to be listened to. On the edge of sleep, this is the place to rejoin. Everything essential is about to be said again, in order, plainly. We began with a suspicion. Gravity, described by Einstein as the pure curvature of spacetime, kept behaving as though it secretly knew about heat. The clearest sign was at the edge of a black hole, where the second law of thermodynamics survives the evaporation of the whole, only because Einstein's geometric equation delivers exactly the right flow of energy across the horizon to keep the entropy books balanced. As if gravity had been rehearsing for thermodynamics all along, when two laws mesh that perfectly, a physicist starts to wonder whether they are really two laws at all. Then we made the suspicion universal. Instead of the one grand horizon of a black hole, we learned to see a horizon at every point in space, the Rindler horizon carried by any accelerating observer, the edge of the wedge cut by the light cone through that point. Every ordinary spot in empty space, including the space just above your resting body, sits on the edge of a latent horizon, waiting for the right motion to reveal it. Then we found, sitting in that empty space, the two things a horizon needs to be thermodynamic. We found a temperature, the Unruh warmth that an accelerating observer feels in the vacuum, and the equivalent fact that the vacuum, restricted to one side of an imaginary wall, becomes a warm thermal state. And we found an entropy, the entanglement entropy of the vacuum, the hidden information locked in the countless correlated pairs straddling the wall, lost to you the moment you seal off one side. Temperature from the Unruh effect, entropy from entanglement, horizon from acceleration, all three, present in nothing, in the plain emptiness of any room. Then came the master stroke. Jacobson took the oldest relation in thermodynamics. Clausius's delta Q equals TdS, heat equals temperature times change in entropy, and demanded that it hold across every one of these local horizons, at every point, in every direction. And out of that demand, with gravity nowhere assumed, came Einstein's field equation. Gravity revealed as an equation of state, a law of the collective, the way the ideal gas law is a law of the collective, a statement about the averaged behavior of some immense number of underlying things, not a fundamental force in itself. And finally, we watched gravity turn around and rescue its own foundations, cutting the otherwise infinite entanglement entropy down to the finite Bekenstein-Hawking value by blurring the imaginary wall at the smallest scales, where the fiercest fluctuations wrap themselves in tiny horizons. Gravity emerges from entanglement entropy, and gravity tames entanglement entropy. Each holds the other in place. Before we go on, let me name the quiet miracle running through all 5 of those steps, because it is easy to miss when the pieces go by one at a time. At every stage, the same 3 characters keep walking back on stage together, a horizon, a temperature, and an entropy, and they refuse to appear separately. Wherever one shows up, the other 2 are already there. A black hole has all 3. An accelerating observer in empty space has all 3. A tiny local patch of vacuum, cut by an imaginary wall, has all 3. And when you insist that these 3 keep the books of thermodynamics together, everywhere, gravity is what you get. It is as though horizon, heat, and hidden information were never really 3 things, but three faces of one thing, and gravity is the shape that one thing takes across the whole of space. That is the pattern the whole night has been tracing, and once you see it, you cannot unsee it. If you are drifting now, on the warm edge of sleep, you do not need to hold any of the machinery. You can let the horizons and the boost energy and the entanglement entropy slip away like the details of a landscape seen from a train window at dusk. Keep only the one soft, strange thing at the center of it all, that the pull holding you down and the spreading out of heat are, somewhere underneath, the same single fact about the universe. The curve of space and the cooling of tea, the fall of an apple and the shuffle of a deck gathered into one quiet law. That is the whole night in a sentence, and it is enough to rest on. Everything else is just the careful showing of how we came to believe it. That is the equivalence, stated once, all at once, as plainly as I can put it. Entropy and gravity are not two neighbours who happen to get along. They are, if this picture holds, one thing. The curvature of spacetime is the thermodynamics of the vacuum's entanglement. The weight that holds you down is bookkeeping about heat and information, carried out by the universe at every point, all the time. That is the sense in which entropy equals gravity. And it is why I said, at the very beginning, that if you do not understand this equivalence, you do not understand what reality is made of, because it says the stage on which all of physics plays out is not a stage at all, but a summary, an average, a rumour of something deeper. But notice that stating the equivalence does not close the story. It cracks it wide open. Because if gravity is an equation of state, there is an obvious and enormous question sitting right underneath. The same question that every equation of state eventually forces. The ideal gas law is an equation of state for a gas, for molecules, for atoms bouncing around. It is the collective behaviour of those specific underlying things. So when we say gravity is an equation of state, we have to ask, an equation of state of what? What is the gas? What are the molecules? What is the immense crowd of tiny underlying things whose averaged behaviour we experience as the smooth curve of spacetime? Jacobson gave us the thermodynamics of gravity. But thermodynamics, historically, has always been a doorway. Behind the thermodynamics of a gas lay atoms. Behind the thermodynamics of radiation lay the quantum. So behind the thermodynamics of spacetime, there must lie something. In the second half of tonight, we go looking for it. And the trail leads somewhere I suspect you will not expect. It leads to the possibility that space itself, the very distance between you and the far wall of your room, is woven out of that same quantum entanglement we found hiding in the vacuum. That the fabric is stitched from the threads, and that if you cut the threads, the fabric tears. We ended the first half with a question that sounds almost childish until you realize no one can fully answer it. If gravity is the equation of state of something, what is the something? What is the hidden crowd, the collection of tiny things whose average behavior we feel as the curve of spacetime? And the trail of clues we have been following all points in one direction, toward one answer, strange as it is. The something is entanglement. The crowd is the web of quantum correlations in the vacuum. And if that is right, then it is not only gravity that is emergent, it is space itself. The distance between things, the plain, obvious, seemingly bedrock fact that the far wall of your room is over there and your hand is over here, may be built out of entanglement, the way a woven cloth is built out of thread. To feel why anyone would believe such a thing, let me take you to a piece of reasoning that has reshaped how a whole generation of physicists thinks about space. It comes most sharply from work by the physicist Mark van Raamsdonk around the year 2010, though it grows out of a larger movement of ideas. Van Raamsdonk asked a deceptively simple question. We know that in these systems, two regions of space are connected. You can travel from one to the other. There is a distance between them. They are neighbors. And we know those same two regions are entangled, their vacuums correlated across the boundary. So what happens, he asked, if you imagine slowly turning down the entanglement between the two regions? What if you reduce the correlations, thread by thread, and watch what it does to the geometry? The answer he found is one of the most vivid images in modern physics. As you reduce the entanglement between two regions, the space connecting them stretches and thins and pinches, the two regions drift apart in the geometry, the bridge between them narrowing like a neck of taffy pulled from both ends. And when the entanglement drops all the way to zero, when the two regions are completely uncorrelated, the space between them pinches off entirely. They cease to be neighbors. There is no longer any distance between them, because there is no longer any connected space linking them at all. They become, geometrically, two separate universes that simply do not touch. Remove the entanglement, and space tears. Connection in space is entanglement, and entanglement is connection in space. They are the same fact told in two languages. Take a breath and consider how strange a claim that really is, because familiarity can smuggle it past you before you notice. We have always pictured entanglement as a spooky connection between things that sit in space, two particles, over here and over there, linked across a distance. But this reverses the whole picture. It says the distance itself, the over here and over there, is made out of the entanglement. The connection is not something that reaches across space. The connection is what space is. Distance is not the stage on which entanglement is performed. Distance is entanglement, viewed from far enough away that you see the woven whole instead of the individual threads. And that means the reassuring solidity of the space around you, the plain fact that your bedroom hangs together as one continuous place, that you could walk from one wall to the other through an unbroken stretch of room, is not a given at all. It is an achievement, held up moment to moment by an unimaginable density of quantum correlations, linking each tiny region to its neighbors, everywhere, all the time. Physicists sometimes put it as a slogan that sounds like poetry, but is meant as physics. The universe sews itself together with entanglement. Where two regions are richly entangled, they are close. Where the entanglement thins, they drift apart. Where it vanishes, they cease to be neighbors at all. The map of what is near to what which is to say, the very shape of space is nothing but a map of where the vacuum's correlations are strong and where they are weak. And if that map is drawn by entanglement, then space is not fundamental. It is downstream of something quantum, exactly as Jacobson's thermodynamic argument suggested it must be. Now, I want to bring this all the way home, back to the imaginary wall, because this is the second scene moment of the night, and it is the one where the whole picture becomes something you can feel in your own room. Remember the wall, the flat plane, we drew straight down through the middle of the space around you, dividing near from far. Remember that the two halves of the vacuum, on either side of that plane, are threaded together by entanglement, countless correlated pairs holding one side to the other. I want you to imagine, lying there in the dark, reaching in with an impossible pair of scissors and beginning to cut those threads, one by one, at first. Snip, snip. Each cut removes a little of the correlation between the near half of your room and the far half. And as you keep cutting, as the entanglement between the two halves drains away, the space itself begins to respond. The far wall does not move away in the ordinary sense. It is worse and stranger than that. The very connection between here and there starts to give way, the distance between the two halves of your room beginning to lose its meaning, until with the final threads cut, the two halves of the space simply come apart, no longer near, no longer far, no longer joined by any space at all. You would not have opened a gap in the room. You would have unmade the room's togetherness, revealed that its wholeness was never a given, It was the pull of those hidden correlations, holding here next to there. This is the emotional weight I most want you to carry out of tonight, so let me state it without any hedging. The emptiness between things is not a backdrop. It is a fabric, and the fabric is entanglement. The distance from your hand to the far wall is a measure of how strongly the quantum vacuum is correlated across that gap. Take away the correlation, and there is no across. Space is not the container that entanglement happens inside of. Space is what a certain pattern of entanglement looks like from the large scale. The same way temperature is what a certain pattern of molecular motion looks like from the large scale. The stage on which reality plays out is stitched together from the very quantum connections it was supposed to merely hold. There is a way to check the strangeness of this that Jacobson himself points to, and it turns the scissors thought experiment into something with teeth. Suppose you really did take the vacuum, draw your imaginary wall, and then modify the quantum state to remove all the entanglement across it, disentangle the two sides completely, so that the state on the near side is utterly uncorrelated with the state on the far side. What would you actually have made? The answer is that you would have created a state with, in a sense, an infinite energy sitting on that surface, a violent, extreme configuration whose gravitational effect would be enormous. The very act of cutting all the entanglement across a plane would gouge the geometry so severely that it would tend to cleave the space in two, just as the abstract argument said. This is closely related to an idea that surfaced a few years ago under the name firewall, the notion that stripping the entanglement across a black hole's horizon would replace the smooth, empty edge with a searing wall of energy. The details are still argued over. But the moral is consistent and clear. You cannot separate the entanglement from the geometry because the entanglement is the geometry. Try to tear one and you tear the other. So we have followed the equation of state down to its gas, its atoms, its crowd, and found, astonishingly, that the crowd is entanglement, and the emergent gas is space itself. Gravity is the thermodynamics of the vacuum's entanglement, and space is the shape that entanglement takes. It is an astonishing claim, and if I stopped here, you would be right to be skeptical, because so far it has been a chain of beautiful reasoning without a single place to plant your feet and calculate. But there is one place, one concrete, workable, mathematically precise example where physicists can actually do the sums and watch space emerge from entanglement in front of them. It is a strange and simplified model universe, but it is real mathematics, and it has become the laboratory where these dreamlike ideas are made exact. That is where we turn next. Everything I have told you so far has a quality that should make a careful listener uneasy. It is gorgeous, and it hangs together, but it has been almost entirely a story of reasoning and analogy. Gravity looks like thermodynamics, entanglement looks like connection, space looks emergent. A skeptic would be right to want more. Is there anywhere physicists can actually get their hands dirty, set up the mathematics precisely, and watch a spacetime with gravity in it be built, provably, out of a quantum system with no gravity and no space? Remarkably, yes, there is exactly such a place. It is not our universe. It is a simplified model, a kind of mathematical laboratory, but inside it, the wild claims of the last few parts become theorems you can prove. The model goes by an intimidating name, the ADS, CFT correspondence, discovered by the physicist Juan Maldacena in 1997. I will not drag you through the machinery, because the channel has wandered those particular halls before, and the details are not what matter tonight. What matters is the shape of the thing. On one side, you have a quantum system, particles and fields, obeying quantum mechanics, with no gravity at all living on the boundary of a region, like a quantum film painted on the surface of a soap bubble. On the other side, you have a full spacetime, with gravity, with curvature, with everything general relativity describes, filling the inside of the bubble, the bulk. And the astonishing discovery is that these two descriptions are exactly equivalent. They are the same physics, written two ways. Everything happening in the gravitational interior can be perfectly translated into the language of the gravity-free quantum system on the boundary, and back again. The spacetime in the middle, with its gravity, is not fundamental. It is a re-encoding of the quantum information living on the boundary, which has one fewer dimension. Gravity, in this model universe, genuinely emerges from a quantum system that contains no gravity. And here is where it touches everything we have been saying. Inside this model, physicists proved a precise relationship between entanglement on the boundary and geometry in the interior, a result found by Shinsei Ryu and Tadashi Takayanagi in 2006. The rule they discovered is beautifully simple. Take a region of the boundary, ask how entangled it is with the rest, and that amount of entanglement equals the area of a certain surface in the interior divided by 4. There is that fraction again, the area over 4. The very same relationship we met at the black hole's horizon, the same one hiding in Jacobson's local horizons. Here it is, made exact, tying the entanglement of a quantum system directly to the area of a geometric surface. Entanglement and area, information and geometry, provably the same currency, converted by that same simple exchange rate. This is the concrete, calculable heart of the claim that space is built from entanglement. In this model, it is not a metaphor, it is a proof. And there is a reason I called this part the map with fewer dimensions, because that phrase captures the most disorienting feature of the whole arrangement. The gravitational interior, the full spacetime with all its depth and volume, is completely encoded on a boundary that has one fewer dimension than it does. Everything happening in the three-dimensional inside is written, without any loss, on its two-dimensional surface the way, in an old-fashioned hologram, a flat piece of film can store a full three-dimensional image, so that the depth you see is a kind of reconstruction from information stored on a sheet. Physicists call this the holographic principle, and it is one of the strangest results modern physics has produced. It suggests that the amount of information a region of space can hold is set not by its volume, but by its surface area, the very same area law we first met, all the way back, at the horizon of a black hole. The whisper we heard then, that a black hole writes its hidden information on its skin rather than in its belly, returns here as a thundering general principle. Maybe every region does. Maybe the true reckoning of reality is always done on the boundary, and the roomy interior we live in is the reconstruction. I will not linger longer in this model universe, because it has depths that would take a whole night of their own to explore, and the point for us is narrower and already made. In at least one place where physicists can compute everything exactly, gravity and space genuinely emerge from a gravity-free quantum system, and the bridge between the two is entanglement, measured by area. The dream is made concrete. The equivalence has, somewhere, a working machine you can take apart and inspect. That is what lets us believe the dream might be true of our own universe too, even where we cannot yet do the sums. There is one more piece from this model that I have to give you, because it is the sharpest expression of the whole night's theme, and it carries a phrase you will not forget. It is the idea that goes by the shorthand ER equals EPR, proposed by Maldacena and Leonard Susskind in 2013. The letters stand for two papers, both written, as it happens, in 1935. One, by Einstein and Nathan Rosen, described a kind of bridge or tunnel through space-time connecting two distant regions, what we now loosely call a wormhole. The other, by Einstein, Boris Podolsky, and Rosen, was the paper that first laid out the puzzle of quantum entanglement, the spooky connection between distant particles. For 78 years, those two ideas, the The geometric bridge and the quantum connection sat in completely separate drawers of physics, and then Maldacena and Susskind suggested they are the same thing. That two systems entangled in the quantum sense are connected by a bridge in the geometric sense. That entanglement is a wormhole, and a wormhole is entanglement. Take two black holes and entangle them strongly enough, and a tunnel of spacetime opens between them. The connection you make with quantum correlation and the connection you make with geometry are one connection. It is the tearing space image from the last part, turned inside out and stated as an equation. To entangle is to join in space. To disentangle is to sever space. Now, I have been careful to call this a model universe, and I want to honor that carefulness, because Jacobson does, and it is part of what makes him trustworthy. This beautiful, calculable world is not quite our world. It has a particular kind of geometry, a particular fixed boundary, sitting rigidly at the edge, and our universe does not appear to be built exactly that way. Jacobson finds that fixed, rigid boundary, suspicious it is put in by hand, sitting there unchanging, when the whole lesson of Einstein's revolution was that geometry should never be fixed by hand, but should be part of the living dynamics. So he treats this model the way you would treat a brilliant scale model of a bridge, proof that the design can stand, evidence that the principle is sound, without believing the real bridge will be identical to the model in every rivet. It is a stepping stone, he says, not the destination. But even as a stepping stone, it did something crucial. It let Jacobson sharpen his own argument. In 2015, 20 years after his original derivation, he found a cleaner way to state the whole thing, not in terms of accelerating observers and their horizons, but directly in terms of entanglement. He proposed what he called the maximal vacuum entanglement hypothesis. The idea is that if you take a small ball of space and ask about the entanglement of the vacuum inside it, that entanglement is as large as it can possibly be. It is at a maximum precisely when the geometry obeys Einstein's equation. Gravity is the condition for the vacuum to be maximally entangled, and there was one detail in that result so specific that it haunts him to this day, a detail I find quietly thrilling. The derivation only gives the correct law of gravity if you hold one particular quantity fixed while you do the comparison. Not the radius of the ball, not its surface area, but its volume. Hold the volume fixed, and Einstein's equation comes out perfectly, with exactly the right strength of gravity. Hold something else fixed, and the answer comes out wrong. Why the volume? Jacobson does not know. It is a clue with no explanation yet, a loose thread hanging out of the most successful version of his own idea, the kind of small strange fact that, in physics, sometimes turns out to be the doorway to the next revolution. We will honor that not knowing later, because honest not knowing is one of the most important things this whole story has to teach. But first, we have to look at a couple of the stranger consequences of taking all this seriously, beginning with a quiet little result in the mathematics of gravity that unsettles something you probably assumed was solid, the idea that what is really there inside a region is fixed by what you can measure from outside it. Let me tell you about a piece of pure mathematics that sounds harmless and turns out to be quietly disturbing in the best way. It concerns solutions to Einstein's equations, the actual geometries of spacetime that the theory of gravity allows. You might reasonably assume that if you stood outside some region of space and measured everything you possibly could about it from the outside the gravitational pull, the way orbits bend, every external signature the region gives off, then you would have pinned down what is inside. Surely the outside determines the inside. Surely two regions that look identical from every external vantage point must be identical within. It is one of those assumptions so natural you never think to question it, and it is false. There is a mathematical technique developed by the relativist Justin Corvino around the year 2000 and refined with others that is usually called gluing. What Corvino showed is that you can take solutions to Einstein's equations and stitch them together or reshape their interiors in such a way that the outside is left completely untouched while the inside is made genuinely different. You can build two spacetimes that are, from the outside, utterly indistinguishable, identical in every external measurement, every gravitational signal, every orbit, and yet completely different on the inside. The exterior does not fix the interior. What is really there, deep in the region, is not determined by everything you can learn about it from beyond its edge. Two identical outsides, two different insides, both perfectly legal in the theory of gravity. Sit with how strange that is, because it cuts against something deep in how we expect the world to work. We tend to believe, almost without noticing, in a kind of determinism of the visible, that the full truth of a thing is written on its surface and in its effects, that if you knew everything measurable you would know everything full stop. Corvino's gluing quietly denies it, at least for gravity. It says the interior of a region can hold secrets that make no difference at all to the outside, that identical exterior measurements can hide entirely different interior realities. And this is not a quirk of some exotic edge case. It is a general feature of the mathematics of the theory that governs all of space and time. There is a gentle vertigo in following that thought where it leads. We like to imagine that reality is, at bottom, fully determined, that if you had a complete enough description of the world at its edges, the inside would follow with no freedom left over. Corvino's result whispers that gravity does not quite work that way, that two universes could agree on everything you could ever measure from outside a region, and still differ, genuinely and lawfully, within it. It does not make the theory inconsistent or random. Everything stays exact and rule-bound. It simply means the map from the outside to the inside is not one-to-one, that the exterior underdetermines the interior, that there is a kind of latitude hidden in the depths of space that no amount of outside looking can ever pin down. For a theory as rigid and clockwork as general relativity is usually painted, that latitude is a quiet shock, and one more sign that the solid, fully determined world we picture is a simplification we impose, not a truth the physics guarantees. You can even feel a faint kinship here with the entanglement story we told earlier. There, too, the whole was more than the parts two entangled particles, shared a definiteness that neither one carried alone, so that knowing everything about each separately still left something out. Here, the region's exterior and its interior are like those parts. You can know the outside completely and still not have fixed the inside. Again and again, in gravity and in quantum mechanics alike, the same lesson surfaces from different depths, that reality is more relational, more woven, less reducible to isolated local facts than our plain intuition insists. The world does not store its truth in separate little boxes. It keeps it in the connections. Now, why does this belong in our story tonight? Because it sharpens, from another angle, the same lesson we have been circling all evening, that what is really there is a far subtler question than our everyday intuition assumes. We think of space and its contents as simply, definitely there, with a fact of the matter about every detail, all of it in principle readable from the outside. But the deeper you look into gravity, the more that simple picture frays. The vacuum's contents depend on how you move through it. The entropy of a region depends on where you draw an imaginary wall. And now, the very interior of a region turns out not to be fixed by its exterior. Layer after layer, the notion of a plain, definite, fully knowable reality behind the appearances comes apart in your hands. Not into chaos, the mathematics is exact and lawful at every step, but into something far more subtle and relational than the solid world we imagine we live in. It also connects to a theme that will matter greatly in the final stretch. The difference between questions that are truly meaningful in the theory of gravity and questions that only seem meaningful. If two spacetimes are identical outside and different inside, then asking what, exactly and absolutely, is at this precise point deep in the interior may not have the clean, observer-independent answer you assumed it did. The answer can depend on choices on how you set up your coordinates, on what you tie your measurements to in ways that have no analogue in ordinary gravity-free physics. Gravity makes the very act of pointing to a place and asking what is there more delicate than it has any right to be. And that delicacy, that subtlety about which questions genuinely have answers, is about to resolve one of the most famous paradoxes in all of physics. A paradox that has tormented brilliant people for 50 years, and that dissolves, at least in one influential view, the moment you realize the question behind it was quietly malformed. Hold on to the image, though, because it is a gentle and useful one to drift on. Two rooms, sealed, identical from every angle you could ever measure from outside, and different within, in ways the outside can never betray. The surface does not settle the depths. In a universe where space is woven from entanglement and gravity, is the thermodynamics of the vacuum that is not a bug or a paradox. It is exactly the kind of thing you should expect. And it prepares us for the strangest and most freeing idea of the night, that some of the deepest puzzles in physics are not hard problems waiting to be solved, but confused questions waiting to be dissolved. There is a puzzle in physics so famous and so stubborn that it has consumed the careers of some of the finest minds of the last 50 years. It is called the black hole information paradox, and the channel has spent a whole long night with it before. So tonight I will not walk its full length again. I only want to show you one thing: how the equivalence we have been building all evening quietly changes what the paradox even is. Because there is a point of view, and it is the one Jacobson leans toward, in which this monstrous paradox is not a hard problem waiting for a heroic solution. It is a confused question, and the confusion is the whole of it. Let me sketch the paradox in its barest form. Quantum mechanics has a rule at its very foundation: information is never truly lost. States evolve in a way physicists call unitary, which is a technical word for a simple promise whatever the universe is doing. In principle, you could always run the movie backward and recover exactly what you started with. Nothing is ever fully erased. But a black hole seems to break that promise. Throw something in, let the whole slowly evaporate away into Hawking radiation, and that outgoing radiation looks completely random, carrying no trace of what fell in. When the whole has finished evaporating and vanished, the information about whatever formed it appears to be simply gone, wiped from the universe. So we have two things. Physicists trust deeply the unitarity of quantum mechanics and the local reasoning of quantum fields near the horizon, and they seem to flatly contradict each other. That is the paradox. Now here is the move that dissolves it, and it comes from the work of the physicist Don Marolf, though Jacobson draws his own conclusion from it. It rests on a feature of gravity we brushed against in the last part. In a theory with gravity, you cannot pin down where and when something is happening with the same crisp, absolute precision you can in ordinary physics. In gravity-free physics, you can say, the value of this field at exactly this point, at exactly this time, and everyone knows what you mean. But gravity is what physicists call diffeomorphism invariant, which is a formidable phrase for a humble fact. The labels we put on points in space and time are not themselves physical. You cannot refer to an absolute location because the coordinates are just names, and the theory does not care what names you use. To specify where something is, you have to tie it to actual physical stuff, to a landmark, a reference, a system of matter, and that reference has its own gravity, which affects the very geometry you are trying to describe. A consequence of this, which Marolf drew out, is that the true, well-defined observables of a gravitational theory live at the boundary far away, at the edge, where things settle down and you can define quantities cleanly, and the mathematics that governs how things evolve in time turns out to be, in a precise sense, a statement at that boundary, rather than a sum over the interior. Because of this, any information you can properly define at the boundary is never lost. It evolves cleanly into itself, forever, with perfect unitarity. Marolf called this boundary unitarity. At the boundary, where the questions are sharp, there is no paradox at all. Information is conserved, exactly as quantum mechanics demands. But then, what about the other half of the argument, the part that seemed to show information being destroyed near the horizon? Here is Jacobson's reading, and it is the beautiful and slightly mischievous heart of it. That half of the argument was built out of local quantum field theory, out of statements like the entanglement between this fluctuation just outside the horizon and its partner just inside. And in a theory with gravity, that kind of statement is not actually a well-defined thing. It looks well-defined. It feels well-defined. But to make it truly precise, to track every last scrap of entanglement with the infinite precision the paradox demands, you would have to pin down locations and quantities far more sharply than gravity allows you to, without carefully accounting for the gravitational reference frame you are using to point at them. The lost information was never a properly defined, observer-independent quantity in the first place. You cannot lose what was never sharply there to begin with. The paradox arises from taking an approximate, everyday notion of the information here and pretending it is exact enough to build an ironclad contradiction. It is not. So the resolution, in this view, is not to solve the paradox, but to deny its premise, to point out that the question, was the information destroyed, was quietly malformed, resting on a notion of local observables that does not survive the presence of gravity. And if that feels like a cheat, like getting out of a hard question on a technicality, I want to show you that it is actually one of the oldest and most honourable moves in all of physics. Physics has escaped its deepest paradoxes again and again, not by answering the question, but by revealing that the question was wrong. Think of the famous twin paradox in relativity. Two twins, one stays home, one flies away at great speed and returns, and comes back younger. It seems paradoxical only if you assume there is a single universal time ticking the same for everyone, a cosmic clock against which both twins must age equally. And the resolution is not some clever calculation that makes the ages match. The resolution is to realize there is no cosmic clock. Time is not universal. It is a property of each path through spacetime, and the two twins simply walked different length paths through time. The paradox dissolves the moment you deny the false premise that made it seem like a paradox. Or think of an old puzzle in thermodynamics itself, the Gibbs paradox of mixing, which tangled physicists in knots about the entropy of combining two gases until the resolution turned out to be that certain things they had been counting as distinguishable were in fact perfectly identical, so it had been meaningless to count them as separate all along. That is the shape of the deepest progress in physics, over and over. Not the triumphant answering of a hard question, but the quiet, almost embarrassing discovery that the question contained a hidden false assumption, a cosmic clock that was not there, a distinguishability that was not real, a sharply defined information here that gravity does not permit. None of this means physicists have stopped working on the paradox, and I do not want to give the impression the whole thing is neatly finished. It is not. Even granting that information survives at the boundary, there remains a hard and beautiful question of exactly what you would have to measure to recover it, where, precisely, in the outgoing radiation, the lost story is hidden. and in what fantastically subtle correlations. There is real, ongoing work by physicists such as Suvrat Raju and others, trying to pin down the strange boundary quantities that would let you read the information back out, and they turn out to be intricate beyond anything we can measure in practice. So the picture is not that the paradox was a silly mistake. It is that the paradox, stated in its original sharp form, assumed a kind of precise, local bookkeeping that gravity quietly forbids, and once you correct that assumption, the contradiction softens from an impossibility into a hard problem of accounting. The difference between an impossibility and a hard problem is the difference between a wall and a mountain. You can climb a mountain, and the equivalence we have built tonight is exactly what lets you see the false assumption in the information paradox. Once you take seriously that gravity is not fundamental, that spacetime and its sharp local labels are emergent and approximate, you stop expecting the infinitely precise local questions to have infinitely precise answers. The paradox does not get solved. It gently evaporates, along with the assumption that held it up. And that leaves us, in the final stretch of the night, standing in front of the deepest question of all, the one about what spacetime really is underneath, with a strange and humbling realization about where exactly we stand in the history of physics. We have arrived at the edge of what anyone knows. Everything from here on is honest frontier ideas being argued over right now, in seminar rooms and papers, with no settled answer. And I want to take you there, not with false certainty, but with the particular thrill that comes from standing at a boundary and feeling how much is still dark. To do it, I have to tell you something surprising about thermodynamics, the very science that started us on this path. Thermodynamics has a strange and wonderful property. It is often right, even when the picture underneath it is wrong. It is, if you like, a forgiving science, one that can hand you the correct answer while you hold a completely mistaken idea of what is really going on beneath. The history proves it. Consider Sadi Carnot, the French engineer who, in the 1820s, worked out the maximum possible efficiency of a heat engine, a result so fundamental that we still teach the Carnot cycle today, 200 years later. He got it right. Genuinely, permanently right. But he got it right while believing in a substance called caloric, an invisible fluid that he thought heat was made of, a fluid that flowed from hot to cold and was never created or destroyed. There is no such fluid. Caloric does not exist. Heat is not a conserved substance. It is the disorganized motion of particles, and it can be created and destroyed, turned into work and back. Carnot's underlying picture of reality was simply false, and yet, resting on that false picture, he derived a law about heat engines that was exactly, enduringly correct. Later physicists, Clausius, Kelvin, came along and fixed the foundations, replacing the imaginary fluid with the real statistical motion of molecules, and in doing so, they built the modern science of thermodynamics and, eventually, statistical mechanics. But Carnot had the right answer first, carried there by thermodynamic reasoning that did not need the true microscopic story to work. It happened again, even more dramatically, at the birth of quantum physics. At the end of the 1800s, Max Planck was trying to understand the glow of a hot oven, the way heated objects radiate light across different colors. Using thermodynamics, he found a formula that fit the glow perfectly, the Planck distribution, still in every textbook. It worked flawlessly. But when Planck tried to explain why his own formula was right, to derive it from the physics of his day, he found he could not. The formula that worked could only be justified by introducing something outrageous, the idea that energy comes in discrete lumps, in quanta. Thermodynamics had handed him a correct formula whose true foundation required inventing quantum mechanics, the greatest revolution in the history of physics. Once again, the thermodynamic reasoning ran ahead of the microscopic understanding. The answer arrived before the explanation. Now, You can feel where Jacobson places his own work and why he is so careful and so honest about it. He suspects he is in the position of Carnot. His thermodynamic derivation of gravity may be capturing something genuinely and permanently true, the equation of state, the law of the collective, while the true microscopic picture of what space-time is actually made of remains unknown, and while some of the specific assumptions he made along the way may turn out, like caloric, to be wrong. Thermodynamics is fault-tolerant. It can be right about the law while wrong about the substance. So the fact that gravity emerges so cleanly from thermodynamic reasoning does not tell us exactly what the atoms of space-time are. It tells us there is an equation of state, which means there is something underneath some crowd, some gas, but the identity of that gas is the open question, the caloric versus molecules question, sitting right at the frontier. What might the something be? Here Jacobson offers an analogy I find quietly haunting, and it is worth lying still for. Think of a very cold, very special fluid that physicists can make in the laboratory. A Bose-Einstein condensate a cloud of atoms chilled so close to absolute zero that they merge into a single quantum fluid. Now, that fluid can carry sound waves, ordinary sound, ripples of pressure moving through it. And if you ask whether that sound is quantized, whether it comes in discrete packets the way light comes in photons, the answer, at the scales where sound makes sense, is yes. There are quanta of sound, called phonons, and they are perfectly real. You can count them, scatter them, treat them as particles. But now try to look at a sound wave with a shorter and shorter wavelength, probing finer and finer detail, and at some point the sound simply ceases to exist. There is no such thing as a sound wave shorter than the spacing between the atoms. Look closely enough, and the sound dissolves, and all that is really there is individual atoms, jostling. The phonon is real, and useful, and lawful, and also not fundamental. It is an emergent ripple in a medium made of something else entirely. Jacobson's suggestion is that the graviton, the supposed particle of gravity, the quantum of the gravitational wave, may be exactly like the phonon, real and useful and quantized at the scales we can reach, a perfectly good particle for all practical purposes, and yet not fundamental at all. Probe finely enough, get down to the scale where space-time itself goes fuzzy, and the graviton would dissolve, the way sound dissolves into atoms, revealing whatever space-time is truly made of underneath. We would have been studying the phonons of space-time and mistaking them for the bedrock, when the bedrock was something we had not yet imagined. And what is that something? Here the honesty becomes total, and I think it is the most valuable thing I can leave you with tonight. Nobody knows. Jacobson does not know. He has hunches, he suspects. For instance, that space-time will turn out to be discrete at the deepest level, built from some finite, countable structure, rather than the smooth continuum of real numbers we use today. He points out that the smoothness we assume, the idea that between any 2 points there are infinitely many more, is a mathematical idealization, an extrapolation of counting that may simply not be how the world is built at bottom. But he also freely admits this is, in his words, almost philosophy, a bias, a leaning, not a result. And whatever the underlying structure is, it cannot be anything simple-minded. It cannot be a naive grid or lattice of little cells, because a grid would pick out special directions and break the beautiful symmetry of relativity that experiment confirms to extraordinary precision. There are even good arguments, from the physicist Don Marolf again, that whatever space-time emerges from must be deeply non-local, that you cannot build it out of separate little pieces, each minding its own business, because gravity's defining features simply refuse to come from purely local parts. The thing underneath must be woven together in a way that does not live at points at all. I should pause here on one particular attempt to push this idea further, because you have very likely heard a garbled version of it, and it is worth getting right. Another physicist, Eric Verlinde, took the notion that gravity is entropic, that it is a thermodynamic emergent effect, and tried to run with it much harder than Jacobson does. Verlinde argued, in work from around 2011, and again a few years later, that if gravity is really an entropic force, then perhaps it deviates from Einstein's and Newton's predictions in just the right way to explain something astronomers have puzzled over for decades. The fact that galaxies rotate as though they contain far more mass than we can see. The standard explanation for that is dark matter, some unseen substance providing the extra pull. Verlinde suggested that emergent gravity itself might account for the discrepancy, with no dark matter needed at all. It is a bold and genuinely interesting proposal. But I want to be honest with you about its status. It is contested, not confirmed. The observational tests have been mixed, and most physicists do not regard it as established. Jacobson himself is careful to say he has not been able to follow Verlinde's version in detail and does not claim it. So hold it as a real, live, debated idea at the frontier, one possible child of the equivalence, and not as a settled fact. The careful derivation we spent the night on does not depend on it. And while we are being careful, let me clear away the most common misunderstanding of this whole subject, the one you will find shouted in comment sections. The claim that all of this means gravity is not real, that gravity is an illusion. That is simply a misreading. Saying gravity is emergent is not saying gravity is fake, any more than saying temperature is emergent means your fever is imaginary. Temperature is completely real. You can measure it, it can burn you, it obeys exact laws, and it is also, at the same time, not a fundamental building block of nature, but the collective behavior of jostling molecules. Both things are true at once. That is exactly the sense in which gravity may be emergent. The weight holding you down is as real as anything in your life. It is simply that its reality may live at the level of the collective, the way the reality of pressure or temperature does, rather than at the level of the fundamental furniture of the world. Emergent does not mean unreal. It means real in a deeper and more surprising way than we assumed. There is a phrase that drifts through this corner of physics, half slogan and half confession: Spacetime is doomed. It means that the smooth space and flowing time of all our equations, the arena we take for granted, is almost certainly not the final layer of reality that some deeper concept, one we have not yet grasped and may not even have the words for, will replace it, and space and time will emerge from that deeper thing the way temperature emerges from atoms or sound from a condensate. And the strange, thrilling, humbling truth is that we are standing exactly where Carnot stood, where Planck stood holding a formula that works, that we can use and trust and build upon, without yet understanding why it works or what lies beneath it. We have the equation of state of space-time. We do not yet have its atoms. We are on the eve of someone's quantum revolution, and we cannot see the face of the person who will bring it. That is not a defeat. It is the most exciting place a science can possibly be. And it means the equivalence we have followed all night is not an ending, but a doorway which brings us, finally, back to where we began, to the weight against your body, and to what all of this actually means for you. We have come all the way down and all the way out, to the edge of a black hole and the edge of what physics knows. And now the long road turns back toward the place it started. Feel again the weight holding you against your bed, the soft, even pressure, the pull you have carried unremarked every second of your life. At the beginning of the night, it was the plainest thing in the world, the very definition of solid, ordinary fact. I promised you that by the end you would see it differently, and now it is time to keep that promise, to say plainly what the equivalence is, and why not understanding it means not understanding reality. Here it is, as directly as I can put it. Gravity is not At the deepest level, a fundamental force reaching out and pulling you down. Gravity is what the universe's drive toward greater entanglement entropy looks like when you feel it from the inside. The curvature of spacetime, the very bending that makes you fall, is the thermodynamics of the quantum vacuum, the collective behavior of countless entangled correlations, averaged into the smooth shape we call space and time. Spacetime is not the stage on which matter and energy perform. It is a summary of what the matter and energy and vacuum are doing, the way temperature is a summary of molecular motion, the way pressure is a summary of atomic collisions. Entropy, gravity, and geometry are three names for one thing. That is the equivalence. Entropy equals gravity equals the shape of space. And now you can see why the title was not an exaggeration. If you do not understand this equivalence, you do not understand reality, because without it, you believe you live inside a fixed container called space, pulled around by a fundamental force called gravity, both of them part of the bedrock furniture of existence. And that picture, beautiful and useful as it is, appears to be a surface. Underneath, there is no container and no force. There is a web of quantum entanglement, and the container and the force are what that web looks like when you stand back far enough to stop seeing the threads. To miss the equivalence is to mistake the woven cloth for a solid wall, the average for the atoms, the rumor for the thing itself. Remember the phrase we carried from the very first black hole, as if gravity already knew about thermodynamics. All night, that as if hung in the air, a coincidence too perfect to be a coincidence. Now we can retire the as if. Gravity did not merely behave as though it knew about heat. Gravity knew about heat because gravity is heat in a form we had not learned to recognize the thermodynamics of the vacuum, keeping its books at every point in space, all the time, silently. The foreknowledge that so unsettled everyone was never foreknowledge at all. It was identity. The two laws meshed perfectly because they were never two laws. So return, one last time, to the weight against your body and let it become what it truly is. That gentle, constant pressure holding you into the mattress is not a rope from the earth tugging on your bones. It is the universe leaning at every point along your body towards states of higher entanglement, the same tendency that spreads the warmth out of your tea and lets the shuffled deck never sort itself, the same second law that governs every candle burning down and every ember going grey. The weight that has held you all your life, that will hold you as you fall asleep tonight, is entropy, felt as gravity. The most ordinary sensation there is turns out to be the deepest law there is, pressing quietly on your skin. You have been resting, this whole time, in the arms of thermodynamics, and calling it gravity, because no one told you its other name. There is something steadying in that, I think, rather than frightening. We tend to imagine that learning the world is stranger than it seemed would leave us unmoored, floating, with nothing solid to hold. But the weight is still here. The floor still holds. Nothing about the equivalence takes away a single real thing. It only tells you what the real things are made of. The universe is not less trustworthy for being woven from entanglement instead of built from bricks. It is only more astonishing that the plainest facts of your body, the pull of the floor, the distance across your room, are not the bottom of the story, but the visible surface of something patient and immense and quietly lawful underneath. And that we, small and brief as we are, have managed to catch a corner of it, to hold the formula that works even before we understand it, and to feel, on an ordinary night, the thermodynamics of the cosmos pressing us gently down into sleep. I want to be careful and fair as we close about what is solid here and what is still a beautiful guess, because the honesty is part of the gift. That gravity and thermodynamics are intimately, exactly related at the horizon of a black hole that is established physics, not speculation. That Einstein's equation can be derived as an equation of state from the thermodynamics of local horizons that is a real, published, decades-old result that has shaped how a generation thinks. That entanglement and geometry are tied together, provably, in at least one model universe that too is real mathematics. What remains open, genuinely open, is the largest question of all, whether this means space-time is truly emergent in our own universe, and if so, what it emerges from. On that, the honest answer is that we do not yet know. The equivalence is not a finished theory of everything. It is a clue of enormous weight, a signpost pointing past the edge of the map, and reasonable physicists still argue about exactly how far to follow it. I would rather leave you with that honest uncertainty than a false certainty, because the not knowing is not a weakness in the story. It is the living edge of it, the place where the next understanding will come from. And notice what the equivalence quietly does to the oldest question there, is why there is something rather than nothing, why there is a universe with shape and extent at all. If space is woven from entanglement, then the very fact that there is a here and a there, that the cosmos has room in it for anything to happen, may itself be a statement about quantum correlation, about the universe being connected to itself, thread by thread, so densely that we experience the connection as distance and the distance as a place to live. The room you are lying in, the space your breath moves through, the gulf between you and the farthest galaxy, all of it, on this view, is the shape of the universe holding its own hand. That is not a scientific conclusion you should take as settled. It is the direction the equivalence points, and it is worth carrying gently into sleep, the way you would carry any large and half-understood beautiful thing. Thank you for staying with me through all of it, from the edge of a black hole to the weight of your own body against the bed. If these slow walks through the strangeness of reality are how you like to drift towards sleep, a quiet like or subscribe genuinely helps the channel grow, and it means more to me than I can easily say. And remember, as you let go tonight, the next time you feel the floor hold you or the covers settle over you, you are feeling entropy wearing the face of gravity. Good night, and may you never feel your own weight in quite the same way again.